This is a 3D spectrum analyzer. It takes music as an input and converts it into cool 3D effects. This one has dimensions of 16 by 16 by 5, a total of 1280 LEDs. In this video, I'm gonna show you how I made it. I started with 2000 diffuse LEDs which I bought on eBay. Because the quality of these LEDs is not the best, they have to be checked for brightness, and the LEDs with a lower light intensity should be removed. Next, the plus and minus pins of the LEDs are shortened. They are not used to make the supporting structure. Instead, I'm using a 24 gauge tinned wire, which I straighten by pulling on both sides of the wire. Wires of different lengths are needed to make the supporting structure, in other words the lattice. We don't want to be able to see the lattice. Because I'm using a black background in my spectrum analyzer, I can paint all wires black, which will make the lattice completely invisible. The first step is to paint only the upper half of the wires. When the paint has dried, the wires are removed and cut in small pieces. Now the fun part can begin. The soldering is done on the side of the wire that is not painted. Here I'm soldering 5 LEDs which have the minus pins connected to each other. I call these the building blocks. As you can see, the upper side of the wire is painted black, and the bottom side is not. Now the plus pins of the LEDs are bent 45 degrees. They will be soldered to the vertical wires of the lattice. Next, I remove all excess wire of the minus pins. All building blocks are now placed in a jig, and the bottom side of the LEDs is now painted black. This prevents the ghosting effect in the lattice, when the light of LED travels to the bottom of the LED above it. You can notice that the connection wire is now also painted black, on both sides. This will make the wires invisible on a black background. Now that we have our building blocks, it's time to solder them on top of each other by connecting their plus pins. Instead of soldering them in the vertical direction, it's easier to flip them and do the soldering in horizontal direction using a jig. This jig consists of two parts. This upper part keeps the distance between the building blocks constant, and the bottom part is just a plate that prevents the building blocks from falling through. Both parts are glued together and the jig is ready. When a building block is placed in the jig, it will firmly stay in place. Now for the connections, we're gonna need some wires which are also completely painted black, except on the places where we're gonna do the soldering. Here I'm drawing the guiding lines with a distance of 1 centimeter from each other. I place the wires on a tape and slide the paper with the guiding lines underneath them. A thin piece of tape is then pasted on the guiding lines. These parts of the wires won't get painted. The wires are painted black on both sides, so when this side dries, the other side is also painted. After both sides have been painted, we get black wires with some shiny connection points, which are used for the soldering. Now we take our jig, place the building blocks in it, together with the wires we just made, and solder the whole thing. Once the soldering is done, we get our first band. I also check whether all LEDs are still working, and cut off all excess wire. Then I use a black marker to mark all soldering connections. The same procedure is repeated for all 16 bands. Before building the box, I made a 3D model of it in Google SketchUp, just to get an idea of the dimensions of the box. This model is then transformed into 2D and cut using a laser cutter. All pieces are then removed and painted black. I'm using a matte paint to prevent any reflections of the light. The box is then assembled using some wood glue, and this is how it looks like. To protect the LEDs, I'm using a sheet of transparent PVC, which I bend using a heat gun and a bending bench. Here's how it looks like on the box. It consists of two parts. The larger part is assembled first to the box with some drilling and screws. Next, I use a rectangular board to straighten the edges of the PVC. This way both parts will fit perfectly. Using some glue, the parts are fixed to each other, and after the glue has dried, the board can be removed. The box is ready, and we can place the LED bands in it. After the bands are placed, the minus wires going to the back side of the box are bent over. The same is done with the plus wires going to the bottom side of the box. The whole thing is now held together just by these wires. Using a 40-way ribbon cable, I make connections to the plus wires on the bottom side. The minus wires going to the back side are connected with straight wires. This way, I get the LED box with 16 independent layers and 80 columns to generate a pattern in each of these layers. The electronics is another fun part of the spectrum analyzer, and before buying any components, I made some simulations to be sure that everything works. This way I get a list of all components that I need. The next step is to design a PCB, which stands for printed circuit board. The components are soldered on the PCB, and the PCB basically provides connections between them. In most cases, a PCB has two layers, a top layer in red and a bottom layer in blue. I print both of these layers separately in black and white. For the manufacturing, the top layer you see here is mirrored, and the bottom layer here is not. To make the PCB, I need a piece of glass that can be recovered from an old painting, a drain opener, which is basically natrium hydroxide. It will be used to develop the PCB. Natrium hydroxide can cause serious burns to the skin, so you have to be careful with it. Ferrochloride is a yellow powder which I'm going to use to etch the PCB. We're also gonna need a phase tanner and a photosensitized PCB. It has a protective coating on it to shield it from the UV light. The phase tanner here is used as an UV light source. The exposure time of the PCB to the UV light depends on two things: the UV light source and its distance to the PCB. So for this particular setup, we need to determine how long we have to expose the PCB. To do that, I print a number of identical PCB layouts on a transparency using a laser printer. The layouts are printed double, and after cutting them out, I align them to create a darker pattern, which will better prevent the UV light from passing through. The transparencies are secured with a piece of tape and placed on a photosensitized PCB. Using another piece of tape, I secured the transparencies to the PCB. A piece of glass and some weights are then placed on top of the PCB for a better contact, and we're ready for the test. For the testing part, I use a piece of cardboard to cover all PCB layouts, except one. When the UV light source is turned on, I start a stopwatch and expose the uncovered PCB layout for 20 seconds. After every 20 seconds, I slide back the cardboard, revealing a new PCB layout. This way I get a number of PCB layouts with 20 seconds of difference in exposure times. Later I found that 20 seconds was too long, and I had to redo the test using steps of 5 seconds. After developing and etching the PCB, which I will show later, I decided to take 40 seconds as the optimal exposure time because it gave the sharpest layout resolution. Now that we know the exposure time, we can start making PCBs for the spectrum analyzer. As previously, I print the top and bottom layers twice, cut them out, and align them to create a darker pattern. Here is the top layer of the PCB and the bottom layer. Next, both of these layers are carefully aligned to each other and secured with a piece of tape. Here is a preview of the layout that will occur on the PCB. Once I have an idea on how the PCB will look like, I make a mark on the transparency. Next, I remove the protective coating on both sides of the PCB and quickly align it with the mark. A piece of tape is then used to secure the transparencies to the PCB. Finally, I place the glass and weights on the PCB and slide it under the phase tanner. The PCB is exposed to the UV light for 40 seconds, which is the time we determined during the test. After 40 seconds, I remove the glass and weights, carefully turn around the PCB, place everything back on it, and expose the other side for another 40 seconds. For the development of the PCB, I use 10 grams of natrium hydroxide for 1 liter of water. The natrium hydroxide should be added to the water and not the other way around to prevent any splashes. The solution is poured in a container, and after dipping the PCB in it, you should immediately see the PCB layout. The dark paint coming off the PCB is the photosensitized layer on the PCB that is destroyed due to its exposure to the UV light. During the development, the destroyed parts of this layer are washed off, revealing the copper layer underneath them. The next step is etching. Here I use 400 grams of ferrochloride for 1 liter of water. This solution works best at higher temperatures, so I pour hot water in a large container and place in it a container with the ferrochloride solution. After dipping the developed PCB in the etching container, the solution will remove all copper it comes in contact with. I slowly move the PCB in the solution to etch it. This process can take some time depending on the temperature of the solution. Because ferrochloride is so corrosive, you should only use plastic or glass containers. Once the PCB is etched, give it a rinse under water and clean it off with some acetone. This will remove the rest of the photosensitized layer on the PCB, so make sure you don't dip it in the etching solution unless you want to remove all the copper on the PCB. The next step is to make holes in the PCB for the connections between the top and bottom layer. Using a clothes hanger, I made a handy tool that helps me to keep the components on their place during the soldering. After the soldering, I check the PCB for any short circuits. Next, I clean it with a flux cleaner and Kim wipes. To prevent the copper tracks on the PCB from oxidizing, I use plastic 70, which serves as a protective coating. Now the PCB is ready. The same procedure is repeated for all other PCBs in the spectrum analyzer. As you can see, 2 layers in the PCB are not always enough, and sometimes you need to make connections using some extra wires. For the microcontroller, I'm using a Pingvino development board. Once the PCBs are made, I drill some holes in them and assemble them to the backplate of the spectrum analyzer using some spacers. I designed the PCBs in such a way that they can be mounted to each other, saving a lot of space. Now it's time to wire the LEDs to the electronics. When all ribbon cables are soldered, I put headers on them using a press. To assemble the knobs, I first make holes using a smaller drill bit, and then a bigger one to finish off the job. There are a total of 6 knobs, which are basically potentiometers, providing control voltages to the microcontroller. The knobs are connected to the microcontroller with a ribbon cable. On the side of the spectrum analyzer, there are a number of buttons and connection sockets. The input voltage of the spectrum analyzer can be anything between 12 and 24 volts. All parts of the spectrum analyzer are now ready to be assembled. The spectrum analyzer is now ready to be programmed. This is a complicated project, and for the sake of clarity, I won't go into detail explaining how the electronics work and how the spectrum analyzer is programmed. For those of you interested, there's a link in the description box which will help you to understand how most of the electronics work. It's based on the LEDCube project. However, the spectrum analyzer is a little bit different from the LEDCube, as it takes a random input to create 3D effects. In the LEDCube project, there is no input signal. Instead, you have a number of pre-programmed effects that keep repeating after each other. The differences with the LEDCube project are as follows. In this project, I used custom-built DC-DC converters to generate 5 volts to feed the LEDs. Next, there is a differential amplifier to convert the audio signal to an appropriate input signal for the Pingvina development board. I also used 80 current sources to force a certain current through the LEDs. This way they will all have the same light intensity. On the top of the spectrum analyzer, there are 6 knobs to adjust different settings. Finally, there's a protection circuit. Due to an error in the software, it's possible that you accidentally destroy the LEDs by overdriving them. The protection circuit prevents this by turning off the LEDs. The activation of the protection circuit is indicated by a red LED on the side of the spectrum analyzer. The protection circuit will keep the LEDs off until the error in the software is fixed and the protection circuit is reset. Now let's go back to the project. In order to convert music into cool 3D effects, we need to determine all frequencies contained in the audio signal. The audio signal you see here contains one dominant frequency and a number of others. As we go from left to right on the piano keyboard, the frequency of the notes increases exponentially. Combined with our ear, which has a logarithmic function, we get a linear relationship between the piano keys, which sounds pleasing to our brain. For example, if we play B2 and C2 on the piano, the frequency difference is 14.68 Hz. When we go 3 octaves higher and play B5 and C5, the frequency difference between these notes is over 117 Hz. Even though there's a large difference between these two numbers, our brain will still hear the same interval. Let's try it on the piano. Now let's play 3 octaves higher. We hear 2 exactly the same intervals. In the spectrum analyzer, the piano keyboard is divided in 16 equal intervals. Each of these intervals is mapped to one of the 16 bands of the spectrum analyzer. There are 2 knobs on the spectrum analyzer, which allows to alter the lower and upper bounds of the frequency spectrum. By turning these knobs, we can set the left and right frequencies of the spectrum window, which can be useful when only a part of the keyboard is being used. The new window is again divided by 16 and mapped on 16 bands. There are 1280 LEDs in the spectrum analyzer. It's obvious we can't use a microcontroller that has 1280 pins to control each LED individually. This is where a method called multiplexing comes in. By displaying each layer in a sequence and doing it fast enough, we can trick the eye into thinking that the displayed image is actually 3D. The method that is used in this project to calculate the frequencies is the constant Q transform, which is often used in music applications. The method takes into account the exponential relationship between the notes and converts it into a linear relationship, making it easier to divide the notes over different bands. All the algorithms, including the constant Q transform, are written in C and programmed on the microcontroller. Once the programming part is over, we can connect the MP3 player to the spectrum analyzer and enjoy the show.